I think it's recording. All right. So this is dynamics, right? We've been talking about, or the topic of this course generally, if you want to summarize it in one sentence, is that we are studying the conditions of moving objects. That's pretty much it. And now to do that, we are using different methods, approaches, different math concepts, Newton's laws, right? Now, what we're going to do today is that, well, so far we have been using Newton's second law directly, right? Newton's second law, it was giving us, or it gives us, a relationship between the acceleration of the object and the external force or external forces acting on the object, right? You had a bunch of external forces acting on the object. Those forces were causing, because they were not, the net force wasn't zero, so that net force was causing an acceleration. So that's what we were studying, right? We were studying the relationship between force and acceleration. Now, we're going to introduce energy methods, right? The name says, as the name says, we're going to be more focused on the energy of the system instead of, we still are going to look into forces, obviously, but instead of acceleration, what energy method gives us? It's a new tool that gives us, or we can come up with the relationship, or we can relate, let's put it this way, we can relate the change in position to change in velocity. Right? We still deal with forces, but instead of acceleration, we're going to find we're going to find the relationship between position and velocity, right? Instead of using Newton's second law directly when we were finding a relationship between force and acceleration. Right, so let me just put everything under energy methods. I guess energy methods. So, as I said, we were using Newton's second law before, just to Newton's second law. Right? Now, previously, we were finding the relationship. So let's put it this way: relate, or not relate. Let's say we relate acceleration to external forces acting on an object. Right? Now, what do you want to do now in energy method? Right? This is before, or could before. Now, what we want to do is that we want to relate change in position to change in velocity, right? Or that's what energy method mainly does for us. Relate change in position to change in velocity. This is now, that's what we're going to do. So we're still studying a moving object, but the tool has changed, right? Instead of that, now we have something different. Now, how do we do that? Well, pretty straightforward. We still start from Newton's second law, right? That there is no argument. We said, well, that's proven. Summation of forces is equal to ma. And we're just going to manipulate that a little bit, move things around to get what we want, to get the relationship between change in position and change in velocity, which basically the fundamental or the base for energy method. I can write this as summation of forces is equal to m dv dt. No argument there, right? Acceleration is the derivative with respect to time from velocity. And I'm going to multiply both sides. Well, you might say, how do they come up with this? But well, that's the approach, the most straightforward approach to go from Newton's second law to the relationship we use for energy methods. There are multiple ways to actually get the energy method, the relationship we use in energy method. But this is, I think, the most straightforward one based on what we've learned before. So we're going to multiply both sides with v, velocity. Right? It's an equality. I can multiply both sides with a variable as long as that variable is not zero. It still can be zero, but then it makes it useless. So summation of forces, the velocity is equal to m dv dt dot v. So I just multiplied both sides by velocity. Right? Well, you can think of this velocity is what? It's the derivative with respect to time from position. Right? So summation of forces time dr dt. And we can do the same thing here. You can think about this one as m dv dt. I can actually write it in a better way. So let's write it this way. You can write it as 1/2 m d dt v dot v. Now, v dot v, the reason I put that 1/2 because when we have v dot v, if I move things together, these two, and take derivative with respect to this one, this becomes v squared, right? V dot v is v squared. If I take derivative with respect to time, we're going to have a 2 in the back. So it's going to be 2m dv dt. To get rid of that 2, I put 1/2 in the back. So I just wanted to move this v next to this one and take derivative from both. So doing that, causing an extra 2 that I had to get rid of to make sure that these two are the same, they're equivalent. So I put 1/2 in the back. A little bit of math manipulation there. And I do it because I want to get into a relationship that is something that's more practical for us and it's easier to implement, right? So what comes out of this is summation of forces is equal to, sorry, this is dr. We can get rid of this dt on this side. You can think about it this way, not exactly mathematically what it should be, but you can just cancel out those dt from both sides. So this one gives you summation of forces times dr dot dr. It's a dot product. It's equal to 1/2 m d or derivative v squared. Remember this r, let me draw it here so we don't get lost. Where did it come from? Remember, this is the same particle we have been looking at, right? We're following its motion. So if this is x axis and this is y axis, and if we had some particle, this is the path of the motion. Let's say it goes from this point to this point. This one was dr, the change in position. This is dr, right? That being, this one being r. Let's see if I can write this one being r1 and this one being r2. This one being r1, this one being r2. Go from point 1 to point 2, r1 to r2. dr shows the change in position. Right, again, we are finding a relationship between change in position and change in velocity. This is what we got, right? This is what we were looking for, this relationship there. Now we can, this is in differential form. We can calculate the integral, take integral from both sides, and I can write it this way. Right? I can write it as summation, integral summation of forces dot dr is equal to 1/2 m. If I take integral from the right side, dv squared dt, well, v squared 1 over, you can, v squared comes out, right? If you take, let me, I don't want to make it crowded, but here you get integral dv squared, right? Then integral and derivative basically cancel out each other. You can just think about v2 coming out, v squared coming out. This becomes 1/2 m v And remember, this is changing from V1 to V2. I'll talk about that. So this one changes from R1 to R2, and this one changes from V1 to V2, and V2 squared minus MV1 squared. So when the particle goes from point 1, which is represented by, right here, this is point 1, this is point 2, which is represented, which its position is represented by R1, to point 2, which is position represented by R2, summation of forces times dr, the vector dr, take that integral from R1 to R2, is equal to the change, or is equal to 1 over 2 mv2 squared minus 1 over 2 mv1 squared. V2 and v1 being the velocities at point 1 and point 2. So this is the fundamental equation that we've been looking for the energy method. So this being, let me put an explanation here. So this side, left side, is being work done by, this is work. What was the definition of work? Remember, even from thermodynamics, you have probably seen it. Force, in engineering dynamics or engineering mechanics, force multiplied by displacement gives you work. Right? Whatever that force is, whatever the displacement of that force is, it gives you work done. So this, the left side, is work done as the work that is done on a particle as it goes or as it moves from R1 to R2, as it moves from R1 to R2. So this is the work done as the particle we're looking at is moving from R1 to R2, or point 1 to point 2. You can think about that. Point 1 being represented by R1, point 2 represented by R2, system. Now, the right side is the change in kinetic energy, right? Kinetic energy, so I'm going to put it here, just as a reminder from physics. Work is force. That's not how you write force. It's force times displacement. Right? So that's why the left side is a definition of work, pretty much. And kinetic energy is basically 1 over 2 mv squared, is half the mass multiplied by the velocity squared. This is something that hopefully you have seen in physics. Expanding those definitions, the left side is basically the work, but in integral form, and we need to write in integral form because depending on the kind of force we're dealing with or the displacement, that integral, the way we calculate that integral might be all different, or better to say, you do not always get a very straightforward, nice force times displacement. And that's why I put it in integral form, in general form. In a simple form, if f is fixed, if it's constant, it comes out of the integral, and then it becomes f integral from R1 to R2 dr. So that if you calculate that integral, it becomes force times displacement, or change in position. Right? It's the same thing, just in integral form, in more general, one step back in more general form. The right side gives you change in kinetic energy, right? Whatever is the kinetic energy of the particle at point 2 minus whatever is the kinetic energy of the particle at point 1. So this is change in kinetic energy. Let's put it this way, as the mass moves from R1 to R2. You can also put mass instead of it here, as the mass moves from R1 to R2. So we started from Newton's second law. We got to the point that now we have a relationship representing the change in position to change in velocity. So this is a new tool we can use to study the conditions of moving objects, topic of the course. Now, you can write this, that's basically how we refer to it, this side as u from 1 to 2, which is basically the work done on the particle from point 1 to point 2. And the right side, you can write it as t from 1 to 2. So the left side says the work done by the force acting on that particle. And the right side says change in the kinetic energy of the particle, right? Going from point 1 to point 2. And you realize that the right side is independent of the path you take, right? It doesn't matter how you get from 1 to 2. You get from point 1 to point 2. All that matters is that you need to know what is the velocity at point 1 of the mass, and what is the velocity of the mass at point 1, and what is the velocity of the mass at point 2. That's all it matters. It doesn't matter how you got there. Left side talks about work, right? The work done from point 1 to point 2. So this equality, says u from 1 to 2 is equal to t from 1 to 2. This is called principle of work and energy. This equality is telling us that work done from the left side by the resultant force, summation of forces, right? Resultant force, remember that, acting on a particle is equal to the change in the kinetic energy of the particle. That's principle of work and energy. So I'm just gonna just, you know, you can, if you want, you can put it as principle of work and energy. And energy. So simply put, it tells us work, not work, work done by, let's say, by the resultant force acting on a particle, right, is equal to, think about it this way, change in the kinetic energy of the particle. Right. So just if someone asks you what is the principle of work and energy, that's pretty much what we derive. Now, a couple of things before we look into how to implement this new tool that we developed from Newton's second law, that gives us, again, a tool or an approach that we can use to study the relationship between change in position and change in velocity of an object. Before we implement this in a couple of examples, a few things we have to keep in mind, right? Related to mostly the left side of this, go back. Related to the left side, right? That integral form, that the trick a lot of time is there. The right side is typically the easier part to deal with. So we're going to spend some time on the left side, explain a few things about it, get a little more comfortable with that integral, and see how can we actually, or what does it do for us. Now, first thing that we have to pay attention to, that dot product, right? Mathematically speaking, that's a dot product. Resultant force dot change in position. So since it's a dot product, it means that if Let me put it under a note here. Note. U from 1 to 2, so I bring it here so we can just look at it. U from, it's the best U I can write, from 1 to 2, from R1 to R2, net force or resultant force dot dr, right? That's the left side of the equation. This is a dot product. That's not really pointing out the dot at all. This is a dot product. Dot product. Going back to some old calculus and math stuff, right? What was a dot product? If you had a dot product, if we had, I'll put review, I guess. If you had a dot product like that, if we, when we're saying A dot B, A dot B, the value for this was A times B times cosine theta, the angle between these two vectors, right? Force is a vector, change in position, which is basically displacement, is a vector. If you have two vectors like A and B, think about it this way, A and B, and this is the angle theta between them. So A dot B was the magnitude of that was AB cosine theta, right? The cosine, the angle between them. Now, when cosine theta is 0, when do we get cosine theta 0? What theta gives us cosine theta 0? You remember that?
90 degrees.
90 degrees, exactly. So that means that when A and B are perpendicular, right, when theta is 90 degrees, this A dot B becomes 0. Just going to keep that here. So what does that mean in physical word for us? That's just mathematics, right? It says if you have a dot product, the magnitude of the result would be 0 if the angle between those two vectors is 90 degrees. So that means that the components of force, go back to U from 1 to 2, that integral. The components of force that are perpendicular to the path do not create any work. Meaning that whenever F, the resultant force, is perpendicular to dr, the displacement vector, whatever component, this force, resultant force can have components, right? If you're in X, Y, in Cartesian coordinate system, you're going to have some X components, some Y components. If you are in polar coordinate system, you're going to have some radial components and theta components. If you're in tangent normal coordinate system, I'll leave that for later. I'll ask you about that. But so if the component of force is perpendicular to the direction of displacement, so if summation of force is perpendicular to dr, then that component of force does not create any work, does not do any work. If you are, think about a very simple example. If you have a box on the floor, right, and you're pushing it with some force, this angle, right? You can decompose it into two forces, in X component and Y component, and this box is moving to the left, right? Because of this force you're applying, the box is moving to the left, to the right. I'm losing sense of direction. That means if you look at this force F, this force is creating, if doing a work, right? But the part of the force that is perpendicular to the direction of the motion, this being the resultant force, you can think about it this way, and this being dr. The part of the component, or the component of the force that is perpendicular to the direction of the motion, perpendicular to dr, the displacement, does not do work. only the part that is not perpendicular does work. Now, in this case, they are in the same direction, so basically becomes FDR, like summation. If you think about this as FY, think about it as FX, this doesn't do work. Doesn't produce work. I think it doesn't produce work, right? Because it's perpendicular to the direction. That dot product becomes 0. Only Fx creates work. So just as a note, this was the note I wanted to talk about. You want to add that explanation, you can just put components. We'll talk about this in the first example we'll look at. We'll see in an example, what do I mean by this? Components of force perpendicular to the path don't produce work. All right, that's the note. Just hold on to it. This is something that matters to calculate the left side. As we said, we are talking about the left side of that equation. The right side is relatively straightforward. Now, I have a question for you. If we are studying the motion, let me see how can I phrase it in a question. If you're studying the motion of a particle in tangent normal coordinate system, how does this rule apply? How does this note apply? Can you come up with a general rule about when we in tangent normal coordinate system? I know that the question is not very well developed, but I hope at least a few of you get where I'm going with this, or can give me some explanation. Right? So we're talking about components of force perpendicular to a path do not produce work. Now, if we are exactly, Connor, that's where I was going. Yeah, I understand that the question wasn't well phrased, but yes. So when you're looking in the motion in tangent normal coordinate system, normal component never produces work, whatever normal component force you have. Right? You just have to be focused on tangent component of the force, and as long as you know the path, how much you moved on the path, like that delta S going from point 1 to point 2. How much is your displacement? Multiply that by a tangential component, you're good, because normal component does not produce work. Just as a note, extension of this note. Well, as the note to a note, I guess. All right, so the first thing I wanted you to know about the left side of the equation. The second thing I wanted you to know is the types of force that we're going to work done by some particular forces, right? So we say in this one, we say net force multiplied by the displacement, or change in position. Now, to make our life a little easier, right, we can at least classify or make it more formal for two types of forces, like work done by gravity and work done by springs. We can at least come up with a relatively straightforward equation for those, so you don't have to calculate the integral for those two forces. You still have to deal with friction. You will see that friction, you have to actually do that integral, or at least relatively get a sense of how to calculate that integral. But at least for two forces, work done by two forces, gravity and springs, we can come up with a relatively straightforward equation. And so that's what I'm going to do. I'm going to put it under work done by particular forces. And we're going to just work done by, I'll just say particular forces. The first one is work done by gravity. Right? Work. This way, work Okay, decide what the color. Work done by gravity or weight. Now, work done by gravity, in a general sense, if I want to draw a coordinate system here, let's say we have X, Y, and Z. And let's say we have X, Y. It's a very ugly coordinate system. That'll do. And let's say we have a path going from 1 to 2, or particle or the mass we're following goes from 1, represented by x1, y1, z1, to x2, y2, z2. And it's going in that direction. You have a particle going in that, following that path. Gravity is downward, so this is going to be your gravity. Think about that as in y direction, downward, so it's negative, so it's minus mg j. Just showing it as a vector in Cartesian coordinate. Now the work done by gravity is basically just u from 1 to 2. If you do that integral, or it's pretty much going downward, that becomes minus mg. You can think about y2 minus y1, right? Going from point 1 to point 2. Integral from r1 to r2, then calculate the integral, the position at point 2 minus multiply the position at point 1. And typically we write this as mg delta h being the change in height. You've seen this before. Now, one thing I wanted to pay attention, because things get confusing later on with positive and negative. When we are following the energy method, right? Later on I'll talk about conservation of energy. But when we're dealing with the energy method, remember, pay attention to this negative. That negative, I'll put it here as an explanation, because I personally sometimes get confused. So I can imagine that can be very confusing. So that negative, we get work done by gravity from point 1 to point 2, should be, that negative should be there, or it should be negative if the height increases. So let's put it this way, that work should be negative if height increases. And then negative multiplied by the negative in the back gives you positive. And it should be positive, and I'm talking about this part, positive if height, I'm trying to, height, as nice as I can write at this bottom, height decreases. We'll see in examples, I'll emphasize this, I'll come back to this and I'll show you what I'm talking about. But this is the work done by weight or gravity. Just pay attention to a negative in the back. In this case, we are going downward, right? We're going from y1 to y2, so it's going downward. There is a negative in the back, right? So just keep that in mind. But technically, y2 minus y1, y2 is lower than y1. Right? So the what comes out of that parenthesis is negative multiplied by the negative in the back. This becomes like positive. That's why I put it the positive if height increases, negative if height increases. So in this case, the height is decreasing, it should be positive. I'll emphasize this again when we get to, because I know that that's from experience, that is a confusing part. All right, so we were talking about the left side, right? We said we were just talking about the left side, that integral. This is the work done by gravity. The second type of work, force, that we can specifically look at and come up with some relatively straightforward relationship for that, is the work done by springs. So work done by gravity, this is the equation you use. And second one would be work done by springs. Right? If you have, let me draw it here. If you have a spring like this, let's say it's attached to some end, these are fixed, and then you have this spring in initial form, and the length of that is S1. Then you stretch the spring, right? The length becomes S2. So we go from 0.1, this being 0.1, this being 0.2, right? You have a spring. The initial length is S1, stretch it. I do have a spring here, but I really don't think I can stretch this. This is a very strong spring. It's also compressive spring. So the initial length is S1, you stretch it, you get to S2. So you know, assuming that you know the initial length and final length, the work done by spring, you can calculate that integral, right? Force of the spring multiplied by the change in displacement or position, take the integral. If you do that, you will get u from 1 to 2 would be 1 over 2k, k being the spring stiffness, right? S2 squared minus S1 squared. Add a few things just to make sure that things are not missing. S1 and S2, you can think about them as values of the right values of the stretch of spring at initial and final position, right? And K being, hopefully you remember that a little bit from statics. K being the spring stiffness, right? Spring stiffness, I'll write it here just in case. Spring stiffness with the unit force over displacement, Newton per meter or pound per inch, pound per foot, whatever unit you use for force divided whatever unit you use for length. So this is the work done by spring. One thing you have to pay attention is the stretch of the spring. What is the S1, what is S2? You always need to know these two. Like whether it's given or you have to find it. Spring stiffness is really constant, obviously. If you have enough information, you might be asked to find it, or it might be given as part of the problem statement. So to wrap up the theory part, that before we start looking into examples. Energy method. We are finding a relationship between change in position to change in velocity. We got that red boxed equation there. Work done as mass moves from R1 to R2 equal to change in kinetic energy as the mass moves from R1 to R2. U from 1 to 2 is equal to T from 1 to 2. T from 1 to 2, kinetic change in kinetic energy. Well, as long as you know the velocity at 2 points, you're good. Work done can be a little tricky. A couple of things you have to keep in mind. Two things we talked about. First is remember that the component of force should not be, let me phrase it the way we did it. Components of force perpendicular to the path do not produce work. So when we calculate that integral, we have to keep that in mind. And we said we can also calculate that integral for common forces. Two common forces that you will see is the work done by gravity or weight and work done by a spring. We derive the equations for those as well. Basically, if you calculate that integral for these two forces, you'll get these relationships, right? So if you have these two forces, you don't need to calculate the integral. Just plug in these values, work done by gravity and work done by spring. Just a couple of things you have to pay attention. I'll go over them in the examples, emphasize those notes. But in terms of spring, just remember that S1 and S2 are the stretch of the spring at the beginning and at the end. That's whatever it is. Maybe it has some initial stretch already. You're stretching it more, or has some initial stretch. You're compressing it. Just keep in mind, you have to know S1, initial length, final length, to know how much work has been done from point 1 to point 2. All right. So let's look at a couple of examples. I think examples are easier than it's much easier to follow what we talked about through examples. No, that's how it typically is, obviously. Question on this before I about the theory part of the story. All right, let's see how many examples we get to go over, then I'll do the rest next class. So the first example, we have pretty straightforward, just to get a sense of how do we deal with these forces. We have some inclined surface like this. It's supposed to be a surface. I'm trying to show that. I don't know if I'm making worse. We have a box sitting there on the surface, and it's being pushed by some force F. This angle is 20 degrees. Now, problem statement, you can write the 30 kilogram, I think it's 30. The 30 kilogram box is moving up the smooth, so no need to worry about friction in this case, up smooth inclined surface, inclined, if I can get this, inclined surface. Let's put it this way, let's add to it, at 2 meters per second. The constant force F is equal to 150 newtons. Force is that. How fast the box, or let's put it this way, how fast will the box be moving when it has moved 1 meter up the surface from the, oh, you don't need to put from the present position of the surface. It doesn't really change anything. And that 1 meter, they're talking about this. If I can make a straight line there, there you go. They're talking about this. This is the 1 meter they're referring to. Right. So we're talking about velocity. One sign that one hint that you can get a sense of it's better to use energy method is when you're talking about velocity, some velocity and some position, right? Remember, the energy method supposed to be a tool that you can find the relationship between position and velocity. That's not always easy to get that hint, but in this case, it's pretty straightforward, I think. Since you're given velocity and you're given the position, how much it's moving, so it should give you a sense that, well, we're looking at the relationship between change in position and velocity. Right? So let's form that equation. Right? We said the energy method told us this is equal to 1/2, or let me start even, actually, let me start from a more abstract version. We know U from 1 to 2 is equal to T from 1 to 2. And 1 being where we are, 2 being 1 meter off the surface. So I'm going to split it into different components. I think it's easier to follow. So let's say U from 1 to 2. We have the force F. And we have also weight in this case. This is a box going off, has some mass. So if you think about that, I'll put it, being lazy, I'll put it on top of this. You have a weight downward, mg, and you have that force. So again, I'm going to split it. Let's write it this way. And let's draw a better bracket. Start. U from 1 to 2 because of gravity, I'll call it that way, and U from 1 to 2 because of force. Now, this is going up. Right? Let me just expand everything. Minus mg delta H. It's going to be minus mg H2 minus H1. Let's see where are H1 and H2. I'm going to draw this triangle here. I'm going up 1 meter, and this angle is 20 degrees. This becomes my delta H. That's how much I'm going above the floor or the surface that I am already. You always take where you are as the origin or the reference and see how much you go up. Right? If this is your reference point, right there where you are, you go up delta H amount. Now, what is that delta H? Actually, it's better not to write H1 minus H. Just write it as delta H. What is that delta H? How much I'm going up?
Is it just sine 20 degrees?
It's basically sine 20 degrees, exactly. So minus mg, or this height, would be 1 sine 20 degrees in this triangle, right? Exactly. 1 meter, right? Sine 20 degrees. Now, see, when going up, going back to the note I mentioned here, when going up, negative. Well, the final value you get, the final expression you get has to be negative if the height increases. Here you go. When the height is increasing, the value is minus mg sine 20 degrees. I'm emphasizing this because later on when we move the parameters to the other side, you'll see this positive when we have only conservative forces. This form, U from 1 to 2 is equal to T from 1 to 2. If the height is increased or is increasing, your final value should be negative, or final expression, which it is. Right? Delta H is positive. You have a negative in the back, so it becomes negative. If you were going down, delta H was negative. You had a negative in the back, it becomes positive. So that's it. That's the work done by the weight, by weight. Now, work done by force. This is the other, the note I was mentioning. Now we have a force, and we know dr. This is dr. The component of the force that is perpendicular to the displacement does not do work, does not produce work. So in this case, if you think about this force and decompose it into two components, right? This one and this one and this one. This is Fy. This is, you can think about Fx. Depending on how you take your coordinate. Just think about it. You don't have to put Fx and Fy. I'll just use that notation. It can be anything. What we care about is what is normal and what component is normal to the path, what component is not. So that Fy doesn't produce any work. Only Fx produces work. So if you want to write down the work done by the force, that would be F, and this angle is 20 degrees. That would be F cosine 20 degrees multiplied by delta R or dr, which is 1. Went up. Now you could write this in integral form, right? From 0 to 1, F dot dr. This would be whatever your r is, the change in position. You start from whatever you are. Let's write it this way: r1 to r2. This becomes F delta r. F is constant. You can take it out. It's going to be F delta r. Right? Now this is dot product, so this becomes F delta r cosine theta. Right? You'll get the same thing. It's a dot product. So F is whatever it is, delta r is 1, you get F cosine 20 degrees times 1. That note comes into play here. You'll have to pay attention to the force. As I said, the left side of the equation, there are some tricks there, how to implement it. Thinking about weight, spring, you have any external force, right? Aside from weight and spring, whatever you have to use that integral to calculate. Can be an external force, can be a friction. But if it's weight or spring, we use the equations we already derived. If it's not, you have to think about that integral form and start thinking about whether all the components, which components are perpendicular to the direction of the motion and which ones are not. The ones that are perpendicular do not produce any work. You can always go to the basic definition, calculate that integral and dot product, and say, well, this is a dot product, means components multiplied by cosine angle between them. In this case, the angle between dr and F is 20 degrees. So I put cosine theta and theta being 20 degrees. Once we calculate the left side, the right side is, there is really not that much there, right? You can just say T1 to 2 is equal to, well, we know the mass is 30 kilograms. So we can think about that as 1 over 2m. The initial velocity is given. This is your V1. It's going to be, I can just, since the mass is not changing, I keep it, factor things out. V2 squared minus V1 squared. 1 over 2. The box is 30 kilograms. Final velocity, we don't know. Initial velocity is 2 meters per second, so 2 squared. Now, we just say U from 1 to 2 is equal to T from 1 to 2. Right? And this U from 1 to 2 is U from 1 to 2 because of weight plus U from 1 to 2 because of force. You put everything together, you'll get force is 150. So we get 150 cosine 20 degrees minus That's from mg 30 times 9.81 times sine 20 degrees is equal to 1/2 times 30, so it becomes 15 times v2 squared minus 4. So from there, you can actually find the only unknown you have is v2, like final velocity of this box when it gets all the way. I can actually give you directly the final answer. That'll be, assuming I didn't make any mistake, that would be 2.586 meter per second. This is the final velocity, right? So this example had a couple of things that we wanted to, I wanted to talk about. First, pay attention on all the forces, right? If you have weight or spring, you use the equations we derived. If you don't, any external force, including friction, right, you have to go with the dot product. Now, in this case, well, we said we had a force, had some angle, we dealt dr, right? It's a dot product, so you have to pay attention to the angle between the direction of the force and the direction of the motion, right? You have to always pay attention to that. 20 degrees here, you can do the dot product. If you don't want to do it, think about the note I mentioned. The component perpendicular to the direction of the motion doesn't do work, so the only components you care about are the components that are not perpendicular to the direction of motion. In this case, I decompose it into fx and fy, and I said fy is perpendicular to the direction of motion. I ignore it, I know just fx. So multiply that with change in position. Right. Weight, pay attention, minus mg delta h. So if delta h is positive, meaning you're going up, the work done by weight becomes negative. If delta h is negative, you're going down, the work done, the final value is positive because you have a negative in the back. And that comes from what I was mentioning here, right here. And this is, when I say negative, if height increases, I'm talking about the whole thing. Right? Because of the negative in the back, if the height increases, delta is positive, the whole thing becomes negative. I emphasize that it's positive and negative because that's the main point that mistakes happen when you're using energy methods. Once you know those, kinetic energy is straightforward typically. You can just find the velocity. Question on this one.